Welcome to Resilient PNT 360 and 180, where we give you a 360-degree view of a topic in 180 seconds or less.
So I'm Lisa Perdue. I'm the product line director here at Aurelia for simulation. We launched our existing simulators back in 2010, so it was a fairly old design. And we decided, it was time to update them, but what are we going to do? We want to do something new. We want to do something innovative. And we looked in the market and said, look, there's Skydell. They're already doing something new. They're taking advantage of COTS hardware. They're doing their modulation in GPUs instead of in FPGAs. It's something different, something that no one's ever done before. So it matched perfectly with Aurelia's strategy of innovation and continuing to push the borders of what's possible. When we say software-defined architecture, really what we have is our software. That's where we invest all of our R&D. Right? And we're able to utilize NVIDIA GPUs, which are just off the shelf, and we're able to utilize software-defined radios that are just off the shelf. We can make drivers to utilize many different radios. What that gives us is the ability to have a more powerful platform, more capability, without us having to invest anything in R&D. All we have to do is take the newest, latest, most powerful GPU, use that one instead of a previous generation, and we can choose different software-defined radios based on whether they're what their cost is, their quality, what's available in the market. All we have to do is write a driver for Skydell in order to communicate with it and to have it generate our RF. When we use the software-defined architecture rather than fixed allocated hardware, we're able to take a radio and use it for multiple things. So we can say, okay, we'll take this low-cost radio, we'll use it this time for a jammer, next time for a spoofer, next time for GNSS signals. And because we're using the commercial off-the-shelf radios, they have a higher power level, especially a high power level compared to GNSS signals. So what we're doing is attenuating the signals at the output. That allows us to change that level of attenuation and have a much stronger jammer, for example, than GNSS signals. And we can repurpose that hardware and use it next time, change the attenuators, and use it all for GNSS signals. They're commercial, they're off the shelf. We can take advantage of the high quality radio, but we can use it for jamming signals, we can use it for spoofing signals, we can use it for GNSS signals, and you have that flexibility to do whatever you want with it without having to design a special module, right? I don't have to develop anything for jamming module. I already have it. I just need to attenuate the signal appropriately, combine it with the GNSS signals, and we have a jamming scenario with a very high jammer to signal ratio, much higher than we would be able to get if we were just doing it all on the same exact hardware that was generating the GNSS signals. We wouldn't be able to get that large dynamic range.